Assalamu alaikum ji. This is lecture number 18 of our course, which is numerical methods, and we were doing from last two lectures the topic of the curve fitting. Okay, so just a quick overview of what we have done yet in this particular topic. We started with the two options, that is, one, if you wanted a consolidated behavior of the data, what is the pattern of the data, then the machine learning techniques are a good way to go with. Okay, and the other option is that we wanted to fit a curve with the observation or with the proposition that we also want to do the numerical differentiation and integration. Okay, maybe we wanted to fit a curve, and then I wanted to maybe have the integration of that particular um, curve we have fitted from a certain point to a certain point. Then the interpolation techniques that we are using or doing are the wise way to go with. Okay, so we started with the Lagrange interpolation, polynomials. We have seen how we're going to fit within the data the LIPs of the different degrees. Okay, first degree, second degree, third degree, or higher degrees. And we have seen the alternative form of the LIPs, which is more systematic in calculations. That is the Newton divided difference formula. We have seen in the last lecture. A Newton divided difference formula have three forms, namely forward difference, backward difference, or the central difference. Okay, it depends that from the given data where you wish to have the interpolated value, where you wanted to find the interpolated values, you can use the respective divided difference formula. Okay. Now, coming to the problems that we faced with the Lagrange interpolation and Newton divided difference formula, which is number one, when we have large data, then the polynomial order will be increased. If the polynomial order will be increased, there will be a lot of oscillation in the data within the nodes that we are. We know that within the data points, there will be a lot of fluctuation, oscillation. Okay, so that is not most of the time good. Okay, so to counter this, we will have a strategy of which what we try to do is, rather than just in a whole data just try to plug one polynomial, just try to plug multiple polynomials, okay, of the same degree. For example, if you see this figure, okay, so I have some data points starting from x0 to xn. Okay, so these are the function values at the given data. Okay, so just for the generally speaking, we got data points, namely x0, f of x0, x1, f of x1, and if we keep continue, xn, f of x. Okay, so if I ask you how many data points we have, we got n plus 1 data points. Okay, so there are n plus 1 data points, or you can say observations. And if I just plot them on the graph, okay, so these are the given points, for example. Okay, now as I just told you, just to counter the fluctuation of the higher degree polynomial, what we can do is we can fit the lower degree polynomials within the data. How we can do that? For example, we start with the first degree polynomial. Let's start with the by plugging the first degree polynomial. So for example, between the 2 points, the first 2 points, I plug a straight line. Okay, then in the next 2 points, I got another straight line. Okay, so if I just try to plug these straight lines, okay, so that will be a curve. Okay, but this curve is defined by which thing? there is, let me call s of x as a total um, polynomial that we have constructed, and this polynomial will be s naught of x from point number x naught from the first 2 points. Okay, so let me just say from x naught to x1, s naught will be applicable. So what is s naught, by the way? This straight line is s naught of x, the first straight line. Okay, then we got s1 of x, and s1 of x will be applicable from the point x1 till the point x2. Okay, if we just keep continue like this, there will be sj of x. Okay, sj of x, and if you see, if s naught is applicable from x naught to x1, s1 is applicable from x1 to x2, then sj will be applicable from xj to xj plus 1. Okay, j plus 1. And if I keep continue like this, you see over here, here we have s1 between x1 and x2. So between the point xn minus 1 and xn, uh, we will have s of x with the subscript. What will be the subscript? N minus 1. N minus 1, because with x naught and x1 we got s naught, with x1 and x2 I got s1, so it means for xn minus 1 and xn I got sn minus 1. Okay, so let me just write at the end sn minus 1 of x, and it is applicable from xn minus 1 till xn. Okay, so so it means this s naught is a straight line, this s1 is a straight line, sj is s. These are all the straight lines. Okay, so we connect. Okay, we collected and we connected them together. Okay, so this will be my piecewise function. So we usually call it as a piecewise function, because if we wish to interpolate within the first interval, then we have to use this function. Okay, and if my point where I wish to interpolate lies between any respective interval, then I have to use the corresponding sj. Okay, so this is the piecewise function that we constructed. Now coming to the problems that we encounter. Okay, so with the linear splines, so these are called the splines, by the way. Okay, what are the splines? Splines are when you have linear functions connected together. Okay, so these are the splines. Okay, so by the way, these are the linear splines. So we use linear splines to formulate our polynomial that fit within the data. Okay, now if I just try to see over here, write any of the sj of x. So let me just write s naught of x. So since it is a straight line, so the equation will be like this: a naught plus b naught, and let me say it is x minus x naught. Okay, I just written first degree polynomial. Okay, so if I just write a straight line will have the linear factor and a constant factor. Okay, and I'm just write like a naught plus b naught into x minus x naught, where x minus x naught is the initial point, and we need to determine the values of a naught and b naught, because obviously if this is a straight line, and we can determine the slope, we can determine the intercept through the 2 points that are given x naught f of x naught and x1 f of x1. So we can find that, not a problem for us. Okay, so this is the line which is corresponding to the x naught and x1. By the way, how many unknowns are there? 2 unknowns. Okay, namely a naught and b naught. Okay. Similarly, for S1, there will be A1 plus B1 x minus x1. Okay. So again, we'll got how many unknowns? 2 unknowns. If I just keep continue up till Sn minus 1, so this will be An minus 1 plus Bn minus 1 x minus xn minus 1. So it will also have 2 unknowns. Okay. How many total unknowns we have? How many equations we have? N equations. Total equations are n. So this is 2n. So the total unknowns are 2n. So if I just think like this, if I have 2n unknowns, then I need 2n equations to solve them. Okay, because otherwise I may not be able to find a unique solution. Okay, so if I have 2n unknowns, so I need to have 2n equations. Okay. Now let's coming to how many equations we can develop. Okay. If you see that particular set of data and I just plug in the linear polynomial over here, okay, one observation that you can see from here is one thing, that is if you just see S naught of x, okay, so S naught of x is applicable from x naught to x1. Okay. Now if I write S naught of x naught, what is the value by the way? This is f of x naught. Because as we are in this particular topic, we always say that the function we develop, okay, will always satisfy the given data. So if it satisfies the given data, S naught x naught will give you the value f of x naught. And since the validity of S naught is from x naught to x1, then S naught of x1 will give you an answer f of x1. Okay. Now if I just wanted to see the same information for S1, so S1 starts from x1, ends at x2, and S1 of x1 is same as f of x1, and S1 of x2 is same as f of x2. If you keep continue like this, Sn minus 1, xn minus 1 will be f of xn minus 1, and Sn, oh sorry, am I right? Yeah, Sn minus 1 at xn will be f of x. Okay. So Sn minus 1 at this point will give you the function value at xn minus 1, and Sn minus 1 at xn will give you f of xn. Okay. So these are some things that you got. Okay. How many equations there are? There are 2 equations. Okay. So these are the 2 equations, these are the 2 equations, and finally we got 2 equations from here. So how many equations we have? 2n equations. So these are 2n equations. Okay, because these are the 2 equations. Okay, then we have 2 equations over here, and the total if the total sj's are total n, so if you got 2 equations from every sj, then the total equation you're getting are 2n. Okay, so these are the 2n equations. Now you got 2n equations, you got 2n unknowns, you can solve it and you can find the value of a naught, aj's and bj's. So we have a question that how they are 2n. If you see at s naught at x naught will give you a value f of x naught. Okay, so this is one equation. Okay, so s naught at x1 will give you a value f of x1. So this is the second equation. So from S naught you got 2 equations. Similarly for S1 you'll got 2 equations, and from Sn minus 1 you'll got 2 equations. Totally Sj's are n, so you got 2n equations. Okay, so you got 2n equations, you got 2n unknowns, you'll be able to find them and you can solve it. Okay, now this is something that we can solve, not a problem for us now. Okay, at this point we'll see how to solve it, but at this point we'll be able to solve it since the total unknowns and the total equations are same. Okay, you can just see from here how many equations there are. 2. So we have 2. If you just keep continuing, here we have 2. So if you just add them, okay, this is 2n. These are the 2n equations. Okay, so okay, now a problem come, which is because we wanted a numerical differentiation and integration from this particular curve, we're going to do that. That is our motive. Okay, one of the motive is. Now if you see at this point, do you see a function is differentiable? So these are the corners. Okay, and at the corners the functions are not differentiable. Okay, now if you see, the property of s of x is that it is continuous, it is connected, it is a continuous curve. Okay, but it is not differentiable. So if it is not differentiable, how I'm going to get the idea of the numerical differentiation? Okay, because it is not a differentiable curve. Okay, so that's why the linear splines are not a good option to go with if you wanted a numerical differentiation or integration. Okay, so they are not a good idea. Okay, now coming towards the second degree polynomial. Okay, so if you see, if I just try to fit a quadratic curve, so I just try to have the same data at this point. Okay, and if I just try to have a quadratic curve between the 2 points, then over here, then over here, then over here, then over here. So might be I got a curve like this. Okay, it may be a little bit smoother than the linear curve. Okay, but we'll get such a trend. Okay, now if I ask you that, okay, from x0 to x1 we have s0 of x, from x1 to x2 we have s1 of x, and similarly from xn minus 1 to xn we have sn minus 1 of x. Okay, so my function will be like this. There is no going to change, but what going to change is actually these s0, s1 and sj's, because now I am using a quadratic degree splines. Okay, I'm using a quadratic splines. So if I use that, obviously this equation will be going to change to the quadratic degree. So if I now write another term, which is c0 x minus x0 square plus c1 x minus x1 square and cn minus 1 x minus x n minus 1 square. Okay, so these are the polynomials. Okay, this is the value of s0, this is the value of s1, and this will be the value of sn minus 1. Okay, now let's start the same thing that we did with the linear polynomials. How many unknowns we have? A0, B0 and C0. So there are 3 unknowns. Okay, similarly we got 3 unknowns here, and we got 3 unknowns. If you total add them, they are 3 times n unknowns, because there are total n equations and each equation contains 3 unknowns. So we got 3 n unknowns. Okay, so these are the unknowns we have. Okay, now we need to find them. Okay, this property is same because we want a connection of the points. Wherever s0 is ending, s1 is starting from there. So we need to connect them. Okay, we need to connect them. So this condition is same. Okay, similarly this condition is also same. Okay, so how many equations we going to get? We're going to get 2n equations. Okay, so 2n equations from here. So 3n unknowns. You see, we just change S0, S1 in terms of the polynomial, but obviously for the sake of this discussion that they need to be connected together, they need to be connected. This is the same thing, okay? And how we connect them? We connect them that at S0, S0 at x1 will be same as S1 at x1. That's a connecting point, okay? We try to connect it. And there is one more information, which is S0 at x0, okay, at this endpoint will be f of x0, okay? This is f of x0, okay? You see, this is the connection. This is same as f of x1, this is same as f of x1. So they are giving the same values. The polynomial, the previous polynomial and the next polynomial at that point will giving you a same value. Say, so your two polynomials are connected together, okay? So, but we are also getting some information that S0 of x0 is same as f of x0, okay? So it means from each polynomial we got two information, both at the endpoints. One at x0, one at x1. One at x1, another at x2. Similarly, one at xn minus 1 and at xn, okay? So the total equations we are getting are 2 from each sj. So total sj's are n. So the total equations we're getting are 2n equations. Now you see the total unknowns are 3n, and there is one issue with the linear polynomials, linear interpolation, linear splines, which is the differentiability at the corners. Okay, so how to achieve that? How to achieve that? Let's try to achieve that with the condition that now you see the differentiability is dependent only. We're talking about the differentiability at the interior points. What are the interior points? X1 to xn minus 1. Or x0 and xn are the endpoints. Okay, so if we're talking about the differentiability, first we need to talk about the differentiability at the interior points. So we need to check that either at x1, my function that I'm going to develop, is it differentiable or not? Okay, so I need to check that. I need to check that, is it differentiable at x2? Is it differentiable at xj? Is it differentiable at xn minus 1? How to make sure that? Let's try to do that. So let's start with the first actually interval, okay, and the second interval. The joint point, connecting point is x1. Okay, x1 is a connecting point. So I will say S0 at x1 will have some derivative. Okay, there will be some derivative of S0 at x1. There will be some derivative value. It should be same as S1 derivative at x1. At x1, both should have the same derivative. The value will be same. Okay, we'll take a derivative of them individually and we plug the value x equals to x1, it must be same. Okay, then if we try to go at x2, we'll say S1 derivative at x2 should be same as S2 derivative at x2. Okay, and if we continue this observation, we'll say, okay, this is Sn minus 1. Sn minus 1 is applicable from xn minus 1 to xn. Okay, so I need to talk about the differentiability at this point. Okay, now this point is being Sn minus 2. Okay, at xn minus 1 will have some derivative value. Okay, at xn minus 1, and Sn minus 1 should have the same derivative value at xn minus 1. Okay, so it means the differentiable value should also be same. Okay, so by the way, okay, so I'll talk about by the way later. So how many equations now we got in with this observation? See, total talk about the generally talk about in n minus 1. We got 1, we got 2, okay, and we'll just keep continue up till this particular point. So we got one equation at x1, we got another equation at x2, so we got up till xn minus 1. Okay, so how many equations I got? N minus 1 equations. I got n minus 1 equations. Okay, because I got equation at every interior point. Okay, the total point at n plus 1. So if I just exclude the exterior point, not the exterior, the end points, okay, so they are x0 and xn minus 1, the total interior points are n minus 1. So I got n minus 1 equation. Now if you add to an equation an n minus 1 equation, how many we have? 3n minus 1 equations, okay. How many unknowns I have? 3n. There are 3n unknowns and there are 3n minus 1 equation are still less with one equation, okay. So and there is a problem, which is at this endpoint or at this endpoint I need to impose some condition, because I can impose such condition on this to obviously find that one equation. But if I impose a certain condition at this endpoint or at this point, this will be a one-sided information. I need to impose the condition at the endpoints. Okay, I can't take just I can't just take a liberty of imposing condition either at x0 or at xn. Okay, I need to impose at endpoints. Okay, so I need, if I impose certain condition, then that condition should be on the both ends. If I impose any of the condition, okay, then I can get two equations from there. Okay, because there are two endpoints. So the total equations will become 3n plus 1. Okay, so if I got more equation and less unknowns, I may not be able to reach at the unique solution. I may not be able to find a solution. Okay, because if the equations are more as compared to the variables, okay, so we may not have a unique solution. Okay, unique solution is always possible when the unknowns are same as the equation. This is the first condition. There are more conditions. Okay, so it means there is a difficulty that we see mathematically, in plugging the second degree polynomial. Okay, a second degree polynomial. This is one of a difficulty. Another difficulty we have talked about in the last lecture. So if you what you can have a difference between the x cube and x square is the pattern of x cube and x square and x cube. Okay, so so this is actual issue by which we one of a major issue by which we do not try to use the quadratic splines. Okay, so now I am going towards the cubic splines. Okay, now we just raising our level to these S0, S1 and Sj's to be a cubic splines. Okay, they are the cubic polynomials. Okay. So why will not be able to use, why it will not be a wise choice? Okay, we can use them. Okay, but why it not be a wise choice? Because we got 3n unknowns. Okay, and we got 3n minus 1 equations. So equations are less as compared to the total unknowns. So if I try to find a solution, I'll not be able to find a solution of these AJs, BJs and CJs. Okay, so there will be some unknown value or there may be some multiple options available. If I got some multiple option, that's not a good thing. Okay, I need to do a prediction or integration. I need a definitive answer. Okay, what is that curve? What is the best fit curve? Okay, so I don't want to doubt myself. Okay, another thing is this. if I impose certain condition on the endpoint, because I impose a condition on the interior points, if I impose that condition, I got two more equations. If I got two more equations, still the number of equations are not same as the unknowns. Okay, now we got more equations and less unknowns. Still, we'll be able to come to the same conclusion as from the less equation. Okay, we'll not be able to come at the unique solution. Okay, so I just wanted a definitive value of A naught, B naught, C naught. I can't have a, okay, there are multiple options of AJs and BJs. Okay, we don't want to go at this scenario. Okay, where we have to choose between which is better and which may not be better. Okay, so now coming to the now let's come to a point where we have, okay, this is, I'll just maybe, okay. So now I'm coming to the cubic splines. Okay, we're just raising our order of the polynomial. Okay, so if I just try to write from here, uh, okay, if this s of x is a cubic, it's a we fit a cubic polynomial, then this s naught, s1, these are all the cubic polynomials. Okay, so what is s naught? If I just keep generalizing the concept, so here we have d naught, okay, x minus x naught cube. Okay, then we have d1 x minus x1 cube, and it will keep continuing. Then we have dn minus 1 x minus x n minus 1. Okay, now if I ask you how many unknowns we have in the s naught, we got 4 unknowns. Okay, in each spline I got 4 unknowns, and the total equations are n, so we got 4n unknowns. Okay, okay, if you see this condition, that is a natural condition. Okay, we just see from the linear splines or the cubic spline, this is something which comes naturally, that we need to connect the points. Okay, this is all about the connecting the points, and the value of a function value should be same as the predicted value we got from here. Okay, they must be same at the given points. Okay, so the total equations we're getting from here obviously are the same. Okay, we're going to get the 2n equations, and similarly from here we got n minus 1 equations. Okay, because the total number of points are same. Okay, so the interior points are same. Just what is changing? Our prediction curve is changing. Okay, the data is not going to change. We're not changing in data. We're not changing the total number of points. Okay, so we have n minus 1 equations from here. Okay, now there, how many equations we have at this point? 2n plus n minus 1, we got 3n minus 1. So a lot of equations we need to add. Okay, so actually n plus 1. So what do you see is we impose another condition over here, and this is why I'm going to impose this condition. I'll talk about it, but let me just first plug it over here, which is, okay, at the interior point x1, the derivative is same. Okay, at the interior point x2, the derivative is same. The derivative is same of what functions? The functions which are connecting at that point. Okay, the functions which are connecting at that point, s0 and s1. Okay, now we impose another condition at these interior points, which is, so at s0, at x1, the first interior point, the two polynomials which are connecting are s0 and s1. Okay, this condition we have already used it. Okay, we have this condition over here. So the condition we use is about a second derivative. the second derivative should also be same at the interior points. Okay, if the second derivatives are also same, it means that you want a prediction function which is very much aligned with your original function. Okay, you want a more smoother curve, a more smoother. If the derivatives are same of the connecting curves, if the second derivatives are same, it means your curve is more smoother. Okay, initially you see in the linear corner point, then when you see a quadratic curve, when you make the derivative as same, it will be a little bit more smoother. Okay, and if you take second derivative as same, it will be more actually smooth curve. It can take the turns more easily. Okay, by not having a little bit of a sharp curve. There will not be a sharp curve. Okay, the 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 change will be smooth. Okay, so if we just impose a second derivative condition at all the interior points, okay, we can't talk about it at the end points at this point. Okay, so that is this one. Then at x1, sorry, at x2, sorry, at x2 s1 second derivative, and s2 at x2 second derivative should be same. If we just impose these conditions, it means okay, n minus 2 at xn minus 1 is sn minus 2 minus 1. Yeah. Okay, so these are the conditions that we plug into the interior points. How many equations we're going to get the same? As many equations as we're getting in the first derivative. Total number of equations are the same. Okay, so these are n minus 1 equations. Okay, so these are the n minus 1 equation. Now if I just add those n minus 1 equation over here, so you see we got 4n minus 2. Okay, so we got 4n minus 2 equations, and we got 4n unknowns. Okay, how many endpoints we have? 2. Now if I impose a condition on the endpoint, I will get 2 equations because the unknowns are 2. So what I see in the quadratic polynomial, when I try to impose the condition at the endpoint, the total equations are either increasing, and if I don't impose it, the total equations are less. Now if I impose any condition at the endpoints, they are 2. So if I add that factor over here, so the total equations will be 4n. Okay, so so if I do that, then it is the equations will be same as the unknowns, and we can just solve them. Okay, we'll get a unique solution. So what is the condition that we're going to impose at the endpoints? It's there are many options. There are many options. Okay, there are many options, but mostly used options are called unnatural conditions. Okay, and a clamped conditions. What is a natural condition? The natural condition says the curve at the end point should be straight. Okay, should be straight. So there should not be, for example, there should not be like this behavior. Okay, if at end point I don't see such a behavior. Okay, there will be not much changes at the end point. Okay, so what is a smooth behavior at the end point? That, for example, if the curve is coming, it's coming straight. It is coming straight. Okay, there is not changing at the end point. Okay, no much changes at the end points. Not a behavior like this at the end point. Okay, so there should be a straight line that is coming towards the end. Okay, and how we can achieve that? We can achieve that by making the derivative of s at x naught, which is one of the endpoint, it should be 0, and at the other xn it should be 0, because the second derivative 0 means the curvature is 0. The curvature is 0 means there is not a changing thing happening, much changing happening in the curve. Okay, it's a state behavior. Okay, so these are the natural conditions. Okay, and there are the clamped conditions. It says the derivative at x naught should be known, and a derivative at xn should be known. So this is some extra information that we wanted from the user. Okay, and that's why we usually they demand further information from the data that we usually don't have at times. Okay, so we use the natural conditions more. Okay, because this is the extra information we wanted from user. We don't know what is the derivative at the endpoints. Okay, we just have performed the experiment. Okay, we just noted down that at this T naught this is the temperature, at this T1 this is the temperature. We don't know what is the change at initial, what is the initial change. Okay, we don't know about it, and what is the final change, we don't know about it. Okay, so mostly used conditions are natural condition and the clamp condition. And by the way, you probably doing other courses too, so these are the boundary conditions, because these are the condition imposed at the end points. So these are called boundary conditions. Okay, so there are natural boundary conditions, there are clamped boundary conditions. Okay, so we will impose these two conditions, and with these two conditions we will have total equations as 4n. Okay, and the total unknowns will also be 4n. Okay, okay, so the questions are very much lengthy, so let me just derive the equations by which we'll be doing a problem in the next lecture. Okay, we'll do the problem okay. Okay, if I just consolidate the information that we have just discussed. Okay, we just discussed a lot of information. Okay, so if I just consolidate that information, you'll see in this slide, this is a cubic spline. So if you go back, if you just go to this particular slide, okay, these are the same information that we have just discussed. Okay, that is uh, at each xj, okay, there is obviously some sj. Okay, there is some sj. It should align with the function values, f values. Okay, that was the initial thing that we started with. Then we talk about the derivative at the interior points and the second derivative at the interior points. They should be same. And if you see in the last condition, it says one of the following set of the boundary conditions should satisfy. That is the natural condition and the clamp conditions. Okay, these are natural and the clamp condition. So if we just use these conditions, these equations from A till F, okay, you will be able to get these values of AJs, BJs, CJs, and DJs. Why I'm talking about this? Because if now I just talk about one cubic polynomial, which is a representation of all the piecewise function, it will be Sj of x. Okay, it will be Sj of x, and it is Aj plus Bj x minus xj plus cj x minus xj square x minus xj cube. Okay, and you have first condition, that is s naught of x naught should be f of x naught. Okay, now coming to the first condition, that is at x naught, s naught should give a value f of x naught. Okay, now if I ask you S1 will give what value at x1? It is f of x1. Okay. Similarly, Sj at xj will give you f of xj. Okay, generally talking about. Okay. Now, if you replace x equals to xj over here, let's see. Let's try to see this equation. So here you see. If you plug this x equals to xj over here, all these three terms will go to 0. So the only thing remain is aj. So it means this is same as aj. Okay, AJs are what? They are the unknowns. A naught, A1, A2, A3, they are the unknowns. And it says A naught is same as f of x naught. Okay, so A1 is same as f of x. It means whenever you have a data, the output portion is actually your AJs. So we need to find all the AJs, BJs, CJs, DJs. That is our objective. Okay, so if we found that, we'll be able to find all our prediction function. Okay, that is a cubic spline. So AJs can be derived from the this observation. Okay, there is another observation which is okay. There is another observation which says S naught at x1 is same as S1 at x1. Okay, okay. So generally talking about Sj at xj plus 1 is same as Sj plus 1 at xj plus 1. Okay, so this is something by which we got that second equation. Okay, you see a first equation we got AJs. From here we got that second equation that I've written in step number 2. Okay, then parallel to this we say that the S naught x1, okay, the derivative of S naught at x naught should be same as this one. With this we able to get a form of the step 3, okay, a portion of a step 3. And there is a step 4 that we got from the second derivatives, okay. So you see these 4 actually equations that I've just written on this slide, we will be able to extract them from the observation we have, okay. And if you see on the right top corner, it says a natural spline. Okay, so we'll see in the coming up lecture when we use natural conditions which are second derivative at the end point is 0. Okay, so then we'll able to get this c naught equals to 0 and cn equals to 0. Okay, or cn minus 1 is equals to 0. We will see that. Okay, so just a wrap up in this particular lecture, we able to construct a cubic spline by first identifying that why we can't have the linear splines, why we can't have the cubic splines. Okay, because this is a very, very critical way that you need to increase. Whenever you try to increase the degree of the polynomial, it comes up with a very much fluctuation. So you need to control that, you need to minimize the order of the polynomial, but at the same time, you need a certain changes in the curve. Okay, so with this, the cubic splines are the most viable option at this point for the splines if we're using the splines. Okay, so thank you so much.